Okay, so we have looked at fully associative cache, which is the most flexible, most powerful in terms of performance, but in terms of size is the most big cache. Okay. Let's look at the other stream. So the problem here is you can it gives you high hit rate. It's quite fast because you just need one compare time to determine hit or miss. You can compare them in parallel, right? It's quite good. But these comparators, 28-bit comparators, are huge. If you remember, 1-bit exclusive NOR, you need about 6 NOR gates, 6 NAND gates, right? It's quite huge. So let's look at some of the other stream. Let's give some restriction. Let's simplify the circuit. So in direct mapped cache, for each of the memory block, you allow only one cache block you can go to. Okay? So you give some restriction. So the idea is you have this 28, 2 to the power of 28 cache memory blocks in the memory. You divide this memory into cache size. So you have 2 to the power of 11 blocks, 2048 blocks. You divide by 2048 blocks, 2048 blocks, and so on. Okay? So, for the first 2048 blocks, the first block mapped to the first cache block, the second block mapped to the second block, the last one mapped to the last cache block. The second cache size, the first block is mapping to the first cache block, second goes to the second, and so on. Okay? So, if you look at some memory location, there is only a single cache block this can be mapped to. Okay? You give the restriction. Okay? So how do you identify which cache block you have to look up? Because there is only one location this can be placed in. Then there are 2048 blocks for each cache, right? So among 2048, you have to identify one, right? So from this 28-bit address, maybe lower 11-bit, you have 28-bit, you divide by 11-bit and 17-bit. And this lower 11-bit identify lower or higher, I don't know. Okay, lower 11-bit identify which of these cache blocks. Okay? Understood? So we can now organize the cache. Okay. So you are given 32-bit address as before, and the lower LSB 4 bits are used to identify which byte among these 16 bytes. Right? That's called offset, block offset, right? Among the 16 bytes, which byte? So you need 4 bits. Okay? So next 11 bit tells you which cache block you have to look up, because there is only one location you can be placed in. Right? So from the memory address, you extract this 11 bit, go through the decoder, you identify the block that you need to look up. Right? You know what is decoder? Do you know decoder? 구현. You know what is decoder? You learned digital logic. Decoder is AND gate. So you have 2-bit decoder. I'm giving you pages. we have 4 AND gates. Okay, so you have A, if A, B is 0, 0, you select this AND gate. Right? If A is 0, 1, you select second. So this D0, D1. If A is 1, 0, 1, 0, you select this one. If it's 1, 1, you select this one. D2, D3. Okay? Because each gate is enabled when AB is 0, 0, 0, 1, 1, 0, 1, 1. That's the decoder. 기억나지? This is decoder. You need 11-bit decoder. And you need how many AND gate? 2048 AND gate. Right? Each has 11 input, 2048 AND gates. Right? So you select decoder. And this is the only location you can find your address, right, and your data, right? So how many? So remaining 17-bit becomes the tag. You check, compare the 17-bit, right? If 17 bits are equal, then you have a cache hit, right? That is the direct map cache. 알겠나? 수박 겉핥기를 알지 말고 정확하게 모르면 다 그려봐 한번. So here you need just one computer to determine hit or miss. So the size is much smaller, right? Much smaller. Same 30 kilobyte data RAM, but text size is smaller because you only store 17-bit tag instead of 28-bit. And instead of 2048 computer, you just need one computer. The size is much smaller. So it's quite simple. But the problem is it gives you low hit rate because you have too much restriction. There is only one location this is mapped to. So if you are unlucky, you might access this block, this block, this block, and so on. But even though other blocks are empty, these are all mapped to the same cache block. So it will be all miss because you replace the previous one. Right? These are called conflict miss. Conflict miss. So because of these conflict misses, direct map cache has high conflict misses and it gives you lower hit rate. It's much smaller, right? And 구현. Its direct map cache is faster than, which one is faster? Fully associated cache or direct map cache? To determine hit or miss. You have to think before you answer. Which one is faster and why? No, hit rate is nothing to do with faster or slower. To determine hit or miss, what happened? You have to think. 구현. 차는 자꾸 외우려고 그러는 거야. 그러니까 안 돼. 디자이너, 엔지니어는 think. 왜 히드월 미스하려면 어떤 일이 일어나는지 저쪽에서 생각을 해야 될까요? 뭘 봐? 이걸 보고 생각해. 두진, which one is faster and why?
I guess fully associated caching is more faster.
Faster, why?
because each cache entry is compared simultaneously with
tag.
each NOR gate. Compared.
So you just compare. So both of them require comparison, right? So why free associative cache is faster? It has only one comparison time. I don't know which one is faster, but overall, to determine hit or miss, which one is faster? With direct method cache, you just need one compare.
Direct method cache has low hit rate. So
As I said, hit rate is nothing to do with fast or slow. 창현, which one is faster and why? It's not more faster, it's just faster. Okay, faster, why? That's right, that's right. 구현, pay attention here. Do not look at your slide. You have to pay attention and pay attention to my words. Okay? That's the basic. Okay, if you look at the fully associative cache to determine hit or miss, what you do is you extract this 28-bit tag from your address, right? And you compare with tag in the cache simultaneously, right? They require one comparison time, right? Execution OR gate, right? And then, if it's valid, you can determine hit or miss, right? Just one comparison time, right? But direct mapped cache, what you do is you first extract your index. You should identify, before you compare, you should identify which tag I have to compare, right? So you extract index and you go through the decoder. This takes time, decoding time. After decode, you compare, right? So previous one, just one compare. This is decoding plus compare. So which one takes longer? Which one? Because it requires extra decoding time. Okay? Okay. So it's reasonably fast, but it's slower than fully associative cache. It might be faster than the other cache which we'll study. So this is too much restriction. You only allow only one cache block. Okay? Let's give more freedom. Instead of a single location, let's allow two. It's called two-way associative cache. Instead of single cache block, let's allow four. It's called four-way associative cache. Let's look at two-way associative cache. So we divide 2048 blocks into two banks. Way 0 bank, way 1 bank. Each bank has 1024 blocks. Okay? Okay? And we divide memory into this bank size, 1024, 1024, 1024, and so on. Okay? And the first block in the first bank can go to the first block in way 0 bank or the first block in way 1 bank. There are two locations. Okay, because we divide it into the bank size. Okay? The second block can be mapped to the second block in the way 0 bank or second block in the way 1 bank and so on. Okay? So bank size is 1024. So how many bits do we need for this bank index? We need 10 bits, right? 10 bits determines 1 out of 1024. and this is called set index. So there are actually two-way bank. Each bank contains 1024 blocks, and there is actually 1024 sets. Each set has one block from here, one block from here. Each set has 2 blocks. That's 2A. Okay? And this index is called set index. Set index. So you need 10 bits to determine which set, okay, from the bank. You have to examine 2 bank. And 2 bank, you have to compare 2 tags, right? Because there are 2 locations. Okay? Minji, you learned this from your computer architecture before, right? Your face looks like, I haven't studied this before. What was your grade in the computer architecture in my undergraduate class? A?
Yes.
A. Oh, you forgot. Maybe. Kuyan, understand? So you learn this first from me, right? So you have to know from now, since I have taught, right? I have taught you this. I'm teaching you. So you have to memorize, or you have to understand, right? Cache. Okay, pipeline. Okay, so you are given 32-bit address as before, and the offset is same as before. You identify 1 out of 16 bytes, so that's why you need 4-bit offset, right? Right. That's the starting point of the address. The address is byte address, and depending on the object, you need to extract 4 byte or 8 byte or 1 byte or something like that, right? If it's a character load instruction, it's a load byte, so you have just extract 1 byte and send to the pipeline. Right? If it's instruction address, instruction might be a 4 byte, then you have to, starting from the byte, you have to extract 4 bytes and send to the pipeline, right? For the instruction. Okay? So this address tells you the beginning byte, right? And the size is determined by what kind of object you are accessing, right? And because you have 1024 sets, each set has 2 blocks, you need 10-bit index, right? Using the 10-bit index, you decode and you identify set. This set contains 2 blocks, one from the way 0 bank, the other from the way 1 bank. There are 2 possible locations. This memory address can be placed in, okay? And using this other tag, 18-bit tag, you just compare. And there are 2 possibilities, so you need 2 comparators instead of 1 for 2 associative cache, right? If any one of them is matching, then you have a cache hit, right? So you load 2 blocks, and out of these 2 blocks, you have to select which one based on this computation result, right? So you need way mux, additional mux. Because the data can come from way 0 bank or can come from way 1 bank, right? So for this hit time, you need decoding, compare, and way mux. So this is a little slower than direct math cache because you need extra muxing time. You have to select which bank will transfer the data. Okay? But it can reduce conflict message substantially because if you are mapping to the same block, if you have another location, then you can reduce this message effectively by increasing this associativity. Okay? Oh, okay, I don't have the slide here, but as you increase associativity, you can decrease this conflict message substantially. Okay? And fully associative cache, there is no conflict message. Okay? So, in general, cache message can be classified into 3 different types. Cold start miss, capacity miss, and conflict miss. cold start miss are also called compulsory misses. That means the first access to a block is always a miss because you have never referenced that block before. That you should miss the cache, you should go to memory, right? This is called cold start miss. Cold start, they say the cache is cold at the beginning because they have never brought in any memory blocks before. And when you brought in memory blocks, as times go by, cache is filled with memory blocks, and it said cache is warm. Okay? And so this is called cold start miss. At the beginning, you have many misses because those are the first access to that memory block, and then you miss the cache. Okay? And so even if you have infinite cache, bigger than main memory in your cache, it will miss the cache because you have never referenced that block before. Right? You have to go to memory. That's the cold start miss or compulsory miss. Okay? Usually this compulsory miss is very small because you have lots of locality. You access again and again. So the first access to a block is that accounts for only a small miss. So, okay? Miss ratio is very small. You will study from your undergraduate class. Okay, the second type of miss is called capacity miss, which is sometimes cache size is limited. So somehow, as soon as cache is filled up with memory block, if a new block comes into memory, some of the old blocks should be replaced. Right? If the cache block is larger than the size, then it should remain in the cache. But because of the size, it's replaced. This is called capacity miss. Okay, capacity miss because of the size. Okay? So even if you have fully associative cache, because of size, some of the cache block needs to be kicked out, and it causes capacity miss. The third type of miss is conflict miss, or it's also called collision miss. It's occurred because of conflict mapping to the same cache block. This occurs only for direct mapped cache and associative cache. But for fully associative cache, you have all the freedom. Memory block can be placed anywhere, so there is no conflict miss. The miss occurs due to only capacity or cold start miss in fully associative cache. Okay? Okay, so these are called three miss types for cache. And there is another miss called invalidation miss. Invalidation miss. So if you look at the cache block, there is a valid bit for each block that determines if this block is a valid block or non-valid block, invalid block. Initially, cache blocks are all empty, so the valid block should be set to 0. It means invalid, it means empty. Right? Once you bring in, they mark it valid. Right? Because you bring a new memory block into the cache. But sometimes the cache block needs to be invalidated because of the sharing or coherence issues. And this can occur for uniprocessor and also for multiprocessor, because this is called cache coherence issue. Cache coherence issues. And this is another topic. So I'm teaching you all this processor pipeline and the processor design, except two issues. One is cache coherence, the other is memory ordering, which are related to multiprocessor and are also complex issues. But I do not teach you, but cache coherence is one of my expert area because my thesis was in cache coherence. Let me give you basics of cache coherence. So usually nowadays they have on-chip caches. So you have on-chip cache here and on-chip cache here, and you have memory. So for memory location A, you bring in here and you bring in here. So there are 3 copies of variable A in this system. And this is, you can view them as dual core machine. Right? And the original content was 100. So you bring in 100 and 100. As you execute the program, you update this into 101. Right? And this is the newest copy, but you have not updated memory yet. So this becomes old copy. Right? So when the CPU1 is accessing this location A, you have to access the new one, right? Instead of old one. Okay? This is called cache coherence issues, right? There can be multiple copies of same location, and they have to preserve they have to maintain their consistency, which is they have to maintain their state. They should be the same state, right? This is the inconsistent state. So what you should do is, whenever you do a write into here, you should broadcast this write into other processor, so that they should not use this data. Okay? So in the bus, you have control line called read-write signal. And whenever you have a write, you activate this write signal. I'm doing a write. And there is data address, usually 64-bit system bus. And there is also 32-bit address line. So you announce your address, you announce your write. Okay? And telling that other processor, I'm doing a write into this address. Okay? So CPU1 or CPU0, they should monitor this bus. If there is a write, then you have to get this address, you have to search your cache, and you have to do a tag compare. If I have a matching entry, okay? If I have a matching tag, then I should invalidate, because that is stale. This stale means it's old data. Okay, stale means 썩은, rotten, old data. I have to invalidate. This is called invalidation. Message. Okay? So you have to look at this bus every time. And this is called snoop. Snoop is like you're listening. Okay? If anybody is writing. This is called snooping protocol or cache coherence protocol, snooping. And based on the state, it's called MESI. So it can be modified, exclusive, shared, invalid. So they have extra state. Or sometimes called MOESI, modified, ownership, exclusive, shared, invalid. So there are many protocols have been proposed to maintain this cache coherence, and this is almost standardized. So every processor has this coherence engine. They look at the bus, snoop the bus. Every time they have the write transaction, they have to get the address, and they have to search the tag array, right? And they have to find matching entry. If there is a matching, you have to invalidate. And they, to speed up their cache coherence affects performance, to speed up their cache coherence mechanism, they use some extra state called modified, exclusive, shared, sometimes ownership, proposed by different people. So it's called mesh protocol, MOESI or MESI protocol. Okay, you have to have this modified state at least. So you have valid bit and you have at least dirty bit. Dirty bit means it's been written. It's been written means it's the new data. So when this flag is replaced, you have to write to memory because this is the newest data. Otherwise you lose your data, right? So you need at least valid bit and dirty bit. and you might need extra bit to implement more complex protocols. Okay? This is called cache coherence bus-based, because bus allows this snooping, because bus is a shared transmission line. Everybody can listen, right? If you use point-to-point connection, you cannot do a snooping. You need other coherent protocols. Okay? So anyhow, this is called bus-based protocol. This is all called, even for unique processor, even without other processor, this can happen because of DMA. DMA means some disk device has this DMA controller inside, and they can directly access memory, and they can transfer the new data into memory. And you can update 102, 102 by using the DMA. And your copy in the processor becomes stale. You have to invalidate because of the DMA. Okay? So they should monitor, and if there is a DMA, a write going on some particular address, you have to search and invalidate. Okay, so this coherence protocol engine should be in uniprocessor, single processor system, and also for multiprocessor system. Okay? Clear? And this is called invalidation message. Okay. So cache performance can be viewed as average memory access time. You are trying to reduce this average memory access time, because if the memory access takes longer, it will slow down your processor. Okay? Average memory access time, the equation is hit time plus miss rate times miss penalty. You need to actually look at the cache first, right? If you have one cache and memory, you have to examine your cache, hit or miss. The page hit time, right? You have to examine your cache, right? If you hit, then it can be accessed right away. If you miss, right? If you miss, you need additional penalty. You have to go to memory and get the data. So if your average memory access time with a single cache, if the hit time is 1 cycle, right? It can be expressed into, if the miss rate is 5%, on a miss, if you pay, let's say 400 cycles for memory access, your total average memory access time becomes, this is how many? 구현. 20? So it becomes 21, right? It's very slow, too slow. So for this system, first level cache is not enough, right? You need extra level cache to reduce average memory time, right? So let's say we have a second level cache. Now L1, L2. We have two levels of cache. First level cache is, as before, we pay 1 cycle for hit or miss. And then it has 5% miss rate. And then usually miss penalty, right? But we have second level cache. So instead of miss penalty, we go to the second level cache. Second level cache hit time, let's assume that it takes 4 cycles. Miss rate is much bigger, so miss rate is only 1%. Okay? And we pay miss penalty. Okay? So this miss penalty is replaced by another average memory access time. It's recursive replacement. Okay? So with two levels cache, this becomes 4, this is A. So this is how many? 구현? 0.05 times 8, how many? 0.4. So total? So you can reduce this average memory extent substantially with another level of cache. This might be enough, okay? So they go with two levels of cache. If the 2 levels of cache is not enough, you add another level of cache and can reduce the average memory access time further. Okay? That's the trend. So as memory becomes slower and slower, processor becomes faster and faster. So you need extra gap between processor speed and memory speed. So you are adding this extra levels of cache. So before they didn't use cache before in early 1980s. They have this cache in 1980s, and first level cache was not enough, so they bring in another level of cache. Nowadays, Core i7 has 3 levels of on-chip cache. If that's not enough, they can have maybe off-chip 4th level cache. In the future, we might have 5th levels of cache or 6th levels of cache in the future, because processor speed, according to Moore's law, about 52% per year, right? But memory speed is only 5% per year. It's exponential gap. It's growing further and further, so we need extra levels of cache. So, memory performance, to improve memory system, to improve memory performance, what you should do is you have to decrease your hit time, decrease your miss rate, or decrease your miss penalty, right? You have to reduce your miss rate, reduce miss penalty, or reduce hit time. So we'll study how you can reduce miss rate, how you can reduce hit time, or how you can reduce miss penalty. Okay? So today, let's think about this prefetching first. Okay? Prefetching is trying to reduce compulsory message. Compulsory message, the first access to a block is always a miss, right? Because you have never referenced that memory block before. You cannot avoid. That's why they call it compulsory miss. You cannot avoid. But you can avoid. If you predict and you can bring the memory block ahead before you access, you can bring into the cache beforehand, right? As soon as your program starts, the cache is smart. They start bringing up memory block before you start. Okay? Or before you access some address, they bring in the memory block ahead. Then you can avoid this compulsory miss because you have to bring in the memory block beforehand. It's like before you are hungry, you can buy ramen. Okay? You start stock in your house. Then you don't have to go to GS shop, right? Because you prefetched, you preloaded. That's prefetching, right? Okay. And the most popular solution for instruction fetch is called instruction streaming buffer. This is used for DEC 21064 and also i10 processors. And also i7 processor, they all use this instruction streaming buffer. The idea is quite simple. On a cache miss, you miss the cache, you usually bring a single memory block, right, into your cache. With ISB, instruction streaming buffer, so you have an instruction cache and there is separate buffer called ISB. It may contain multiple cache blocks. Okay? If you miss cache, you do not bring in just a single block, you bring in 2 consecutive blocks. Okay? And the missed block goes into the iCache, the second block goes into the ISB. Okay? Automatically you bring in the next block. That's the ISB. On an iMiss, you fetch 2 consecutive blocks. The target block goes to the instruction cache, the next block goes to the ISB. Okay? So when you look up the cache, you need to look up cache and also ISB at the same time in parallel. Even if you miss cache, you might find the data instruction from ISB because you prefetched before. Right? Okay? So if the request block hits the ISB, then you can send it to the pipeline and also this block moves into the iCache because you access. Okay? And you make another available entry in the ISB. Okay? A single block ISB can catch about 20% of misses. So that's quite efficient, right? You can capture, with a single cache block, you can capture about 1 out of 5 misses using the ISB. And if you have multiple blocks in the ISB, you can reduce further. And this is quite effective and used in most high-performance processors. Okay? So when you look up the cache, you need to look up the instruction cache, and you need to look up the ISB also at the same time. Okay, 알겠지? And it works well with iCache. It's not as effective for data cache, but data cache can also benefit from iCache. So in 1990s, ISB instruction streaming buffer was used for only instruction cache. Nowadays, it starts to be used for data cache as well. When you miss the data, you bring the next block, and there is another buffer. It's not instruction streaming buffer. It might be called as data streaming buffer or whatever, right? It's also used in other data cache as well. That's called instruction streaming buffer. It's hardware-based prefetching because automatically hardware prefetch the next sequential block. Okay? And you can also do software prefetching, which means you have a separate instruction called prefetch. This is different from load instruction. Load means from memory, you load into a register. Prefetch instruction is from memory, you load into a cache, not to a register. Okay? Load into a cache. This is usually non-faulting instruction because this prefetch is to accelerate the processor performance. This is microarchitectural technique, right? If we code exception, then exception actually terminate the program. Some can terminate the program or it causes some problem. So this is non-faulting instruction, which means if you code exception, just ignore. Okay, you do not execute because this is just optional instruction. That's what I mean by non-faulting instruction. Okay? And it works well for stride-based prefetching because data access is usually, they have a stride because stride means if you access A0, A1, A2, A3 and so on, if this array is integer array, then you need to increment your address by 4 because for 32-bit processor you just increment data address by 4 because each data is 4 bytes, right? And this 4 is called stride. Sometimes you access A0, A4, A8, A12 and so on. In the loop you usually have this stride, right? So you can predict. So if you have this loop array and you can predict, maybe in the next iteration this address will be accepted. Using the stride you can insert prefetch instruction by the compiler. Okay? And this is called software prefetching or compiler directed prefetching. And you can use this for data and also for instruction. Where for Itinium processor there is some prefetch instruction for instruction also. Okay? And if you use large cache blocks, it somehow has same effect as prefetching because you bring in more blocks, more data, and more instruction. Okay? Due to spatial locality. So, Pentium 4 with this hardware prefetching, so with ISB, I'm not sure if they use data prefetching, hardware data prefetching or not. They might. Okay? And they can increase performance substantially, right? Usually, performance is better for a floating point application, as low as 18% up to about twice faster because of this prefetching. The memory performance actually is has an impact on overall performance. Okay? For integer, these two applications has 16% and 45% increment, but for other applications it's lower. There are other 15 integer benchmarks, but they did not show the figures. Overall, this hardware-based prefetching of next sequential block, ISB, instruction stream buffer, has a very good impact on performance. Okay? So it's better to be used. Okay? So as I said, instruction queue that decouple front end and from the back end by having 8 instruction buffers. Itanium processor can increase the speed by 8%, the overall speed. And with ISP, they can also performance improvement is quite effective. Okay? And here we'll study maybe next week. And 2 weeks from now, right, 26th of April, we will have an exam. Okay? And the exam will cover the topics until the next week. Next week we'll finish up memory, and if we have time, we'll go to multi-threading. Okay? 여기까지.